Ladies and gentlemen, my name is Wahyudi Parnadi. I am the coordinator this international virtual course, and now I act as a moderator of this session. I'm very pleased to see you here and welcome all of you to this virtual course. This 2 weeks international virtual course is about geophysical for engineering and environmental. So, ladies and gentlemen, our speaker today is Professor Goto.
Yes.
And yeah, I will show first your curriculum vitae, or do you have a curriculum vitae or the data from your side?
Okay. Now I put the URL of my own slide, PDF file on
Okay,
chat.
we have, so please
Yeah.
allow us to share your
Mhm.
curriculum vitae first.
I will all of you can download the PDF file, or after the finishing of lecture, if you want to give slide to the some another student who has absent this lecture course, so I also put my slide on my own website. So from both URL, you can achieve the same PDF file.
Okay, maybe I can introduce your self. Okay, yeah. Okay, maybe I will introduce you first. So, Harmita, could you read the curriculum vitae of Professor Goto, please? Harmita, do you hear me?
Yes, Pak Wahyudi.
Yeah. Could you read the curriculum vitae of Professor Goto?
Yes.
Please.
So, good day, Prof. Tadanori Goto. Thank you for coming in this room. And Prof. Tadanori Goto, his education is a bachelor degree from Kobe University, Japan, and a master degree from Kobe University, Japan, and doctoral from Kobe University, Japan. The position is a professor, Earth Science Laboratory and Graduate School of Life Science, University of Hyogo. The previous publication over 194 publication on ResearchGate and over 859 citations. The skills and expertise, electromagnetism, applied geophysics, exploration geophysics, and earthquake. The latest projects, integration techniques of geological and geophysical data for modeling hydrogeological structures, crystal and fault structures around seismogenic zones, exploration of energy and mineral resources using electromagnetic techniques, and the last is marine electromagnetic exploration method and instrument. So that's all, Pak Wahyudi.
Okay, thank you, Miss Harmita.
You're welcome.
Now, before the presentation begins, let me inform how the presentation will be going on. First, Professor Goto will be invited to present the material. After that, there will be question and answer session, and then followed by photo session, I think. Yeah. Now, allow me to welcome the speaker, Professor Tadanori Goto, to deliver his presentation. Professor Tadanori Goto, time is yours.
Yes, thank you very much for the good introduction. First, I would like to slightly modify my department. My old department name was Graduate School of Life Science, but now, more simply, Graduate School of Science right now. And I got a PhD thesis, not in Kobe University, but in Kyoto University. And some of the students know the Professor Koike had or will be presented in this lecture course. And I'm keep contact with Professor Koike and the other professors in Kyoto University. Now I'm a professor in the University of Hyogo, and I manage the laboratory named the Earth Science. Not associate professor. I have to modify my old slide. I'm professor, and this is my, excuse me. This is my own homepage address, and my major research field is both land and marine with the method of electromagnetics. And there are various targets of my own researches, such as active fault or oil gas methane hydrate and the seafloor mine deposit, groundwater resources, plus geothermal energies. And all of them can be imaged by using EM survey techniques, electromagnetics survey techniques. This is one of the concluding figure of today's talk. I will introduce and explain the details later. This is the transect image of the active fault. Here is the active fault here. And that image is a kind of near surface transect of the crust from the surface to the about 1.5 kilometer depth with width of about 2 kilometers. Such kind of image can be obtained by using electromagnetic technique. Or this is another concluding figure, also will be introduced later. This is the cluster structure beneath Mount Fuji. As you know, the very beautiful Japanese volcano. And here is the summit. Again, by using EM technique, we can image such kind of cluster scale structure with depth to the 50 kilometer with width of about 80 kilometer. So such kind of image is so valuable for various purposes, such kind of the geohazard evaluation by the volcanic eruptions or earthquakes, or finding energy resources. Today's topics, it is a kind of menu for today's presentation. First, I will briefly introduce the physics. And at the beginning, the electrical conductivity or resistivity of rocks will be explained. Then, quite basic theory for the electromagnetic survey will be also presented. Time is limited. I focus only on an EM survey named magnetic survey. Actually, there are various kinds of EM surveys. The magnetic survey has great benefit to get the deeper cluster images. Then I will introduce several case studies for the active fault examination and geothermal examination. Finally, I will make conclusion with future problems. And probably at the end of my presentation, I can keep the time for question and comments from audience. 10 minutes, 15 minutes, I'm not sure. And again, please download the slide. Now again, I put URL to the slide directory and also my own homepage URL, website URL. Okay. Just a moment. I'm checking the network condition. Just a moment. Several ways for my Wi-Fi. Okay, share again. Just a moment. Share the slide again. Okay. First, I will briefly introduce what is electrical conductivity or electrical resistivity. Very simple. Think about such kind of cylinder. Can you hear me? Think about the such kind of cylindrical shaped material block, and the with having area S and length L. The bulk resistance R can be expressed by this simplified formula. Write again. S L I. I believe you can find not only my own slide, but also some my own real-time drawings. Can you watch them? No problem. Okay. If you have problem, please tell me or please type something on chat. So the bulk resistance can be expressed this formula. The coefficient rho is named as resistivity. The resistance R depends on the size of the specimen. However, rho do not have any size dependence. So the material itself has its own resistivity. So it is called as resistivity. Or sometimes people use the conductivity, electrical conductivity, not thermal, not hydraulic, electrical conductivity. But the relationship between the electrical conductivity and the resistivity is so simple as written in this equation. Archie's law, first presented in 1942, or very old, is still alive. What kind of equation? The bulk conductivity can be expressed by three terms. Actually, there are modified version of Archie's law. It is the simplest version, but it is a that is quite basic and but well defines feature of the electrical conductivity. The bulk conductivity can be decided by first fluid conductivity, second porosity, and M. M is called as cementation exponent. And normally, for example, the sediment has the M equal to typically. How about the granitic rock? In such case, 1.3 or 1.4 is common. It depends on the type of rocks or shape of pore spaces. Where is the solid term? As you can understand, the rock can consist from two major parts: water-filled pore and solid matrix. But look at this equation. There is no relating term to solid phase. Of course, in the modified Archie's law, we can add some solid term like this. But basically to say, the major controlling factor is the fluid conduction and the amount of fluid and the connectivity of pore shapes. It is truly called as the cementential exponent. Also, we have to pay some attention to the clay minerals. Why? In the conventional Archie's law, everybody regulates the effect of matrix because most of rock minerals has very low conductivity. So we do not have to take the term for the solid phases. However, clay mineral itself has very high conductivity or low resistivity. Here is the resistivity of material having clay. Increasing the clay contents result in the decreasing of the resistivity. And the type of clay minerals have a large effect to the degree strength of the resistivity. For example, silicite or Monmorillonite one was a famous mineral included in the smectite group. The smectite clay has this strong effect on the decreasing of the resistivity. Key components for electrical resistivity are summarized in this cartoon. First, water or partial melt. These two materials have the fluid conduction plus the conductive near. Again, for example, granite, sandstone, clay sandstone, and so on has a little amount of clay. So in those rock or sediments, we do not have any care to the solid phase conduction. Only the fluid phase conduction are dominant. However, clay mineral or conductive mineral, including the metal, has the large effect in the bulk electrical resistivity. Low content, high resistivity. High content, low resistivity. Checked? Oh, so many. Okay, two participants from two participants comment. Okay, go ahead. So how can we get the electrical conductivity distribution or resistivity distribution below the surface? Drilling is of course effective, but the too much cost and limited locations. So without drilling, how can we get the resistivity distribution below the surface? Now, I will briefly introduce what is the magnetotelix. I believe some of you, or most of you, know the basic concept of magnetotelix. It is very simple. The first, it is not the concept only for the magnetotelix, but a concept for all kinds of EM survey. Okay, first think about the vibration or fluctuation of the magnetic field, natural current in the ionosphere, or artificial current can make the fluctuation of the magnetic field. It is called magnetic signal. Then, since the Earth has the resistivity, not the insulator, so the induced current can be created by the fluctuation of the magnetic field. Such induced current can make the magnetic field on the surface or electric field on the surface. So these two fields can be observed on the surface, Earth's surface, or even on the seafloor, or even in the borehole. Then we can measure the underground structure. Why? Think about such kind of simplified cartoon. Laboratory experiment in the high school days or junior high school days. Remember that. If you move the magnet on the coil, then coil can make the electrical current. Such kind of amplitude of the induced current can be measured by the voltmeter or current meter. If you know the input field and output field, then you can think about the electrical feature of coil. So this cartoon is basically same to such kind of quite simple laboratory experiment. Again, first you need the magnetic signal. It should not be DC. It should be the where? どこ行った? あ、出た. AC magnetic field. Then AC induced current can be formed below the surface. Then magnetic field or electric field can be made on the surface. So you do not have to make drilling to get the underground structures. There are various kinds of EM survey technique. Now we only focus on the MT, magnet telluric survey. Telluric means the electrical field within the Earth. Magnetotelluric. So it is often called as MT survey or MT method. For MT survey, we observe first horizontal magnetic field, normally two components, north-south, east-west. Again, we do not have to measure the DC magnetic field. We only want to guess the AC fluctuation of the north-south and east-west magnetic field. Then we also measure the two components of induced electric field. How can we guess the electric field? Very simple. We put the two paired electrodes separated with distance of more than 10 meters normally. 50 meters better, 100 meters better, but it depends on the availability of site. And in the mountain range, it is quite hard because the flat space is quite limited in the mountain areas. So the shorter electrode spacing should be required, 10 meters, 15 meters, or something like that. The Nernst voltage difference between two electrodes can be divided by the distance of electrodes. Then electric field with unit of volt per meter can be obtained at a site. North-south component and east-west component can be also obtained. So the two component magnetic field and the two component electric field can be simultaneously recorded at a site. Then we can estimate the resistivity. Resistivity can be normally written with rho in Greek words. So the low distribution, resistivity distribution can be obtained. What kind of data can be recorded? This is EM field, magnetic field of east-west component and north-south component, together with electrical field of north-south component and east-west component. And this is a time series. So one day here, how many days? 10 days? I forget. 10 days or 9 days. You can find the periodic change of the magnetic field. This is so-called daily fluctuation or daily variation of the natural magnetic field. Plus, you can find some fluctuation of the magnetic fields. Fluctuations. Such kind of fluctuation can be created by the solar activities. So the high solar activity can make the fluctuation of the magnetic field. It is called as magnetic storm or geomagnetic storms. At that time, you can also find the fluctuation of the electric field. So those similarities strongly implies that the relationship between the magnetic field and the electric field. Yes, it is the induced field. Induced electric field with the direction of EW and NS. Those E field was created by magnetic field perpendicular to the induced E field. So the EW magnetic field can create NS, and NS magnetic field can create EW. Okay? Why? And focus on the magnetic storm. Before the magnetic storm occurrence on the Earth's surface, high solar activity can make the flare. And the solar winds. Solar winds is the flowing plasmas. And such plasma can strongly give the effect to the Earth's ionosphere. Most of you know the natural phenomenon named aurora. Aurora is a natural, fantastic event having the flashing in the air. At that time of aurora, the plasma, solar wind, plasma can be intruded to the Earth's ionosphere. The interaction between the plasma and the ionosphere makes it flashing. It is called aurora. Our ionosphere is naturally has the many amount of the plasmas. So it is quite fantastic because ionosphere is always on our head, about the 50 to 100 kilometer altitude from the Earth's surface. But ionosphere is no visible, clear clear layer a part of the atmosphere. But it has a large amount of ions. So the surprisingly, the electrical current can flow through the ionosphere part, a part of atmosphere. Anyway, due to the large amount of plasmas, ionospheric current can be strongly disturbed. Strongly disturbed. So what's happened? For example, due to the high solar activity, the current within the ionosphere is strongly disturbed. In this case, the eastward current was suddenly generated. Again, it is not DC current. It is the time evolution of the atmospheric current, not this one. Anyway, due to the solar activity, suddenly eastward current, electric current was generated in the ionosphere. So what's happened? Primary magnetic field can be created as ionosphere. So the east-west current can make the AD magnetic field like this. And finally, the northward increasing magnetic field is created. It is called as primary field. Note that no vertical magnetic field are included in the primary field because the ionosphere has the almost uniform ion distribution. So no current concentration in the ionosphere occurred. Then only the horizontal magnetic field can be created due to the sum of such kind of AD magnetic field. Primary magnetic field can arrive to this Earth's surface and also below the surface. Again, this is not a DC magnetic field, the increasing magnetic field toward the north. Then AD induced electric current can be generated due to the primary magnetic field. If you assume the uniform Earth, so vertical electric current can be cancelled as the neighboring blocks. So there are many same eddy currents. And the neighboring block can make cancelling as the edge. So the vertical current can be diminished. And at the infinite depth, the E field should be decreased. Why? I will explain later. Decreased. So you do not have to think about the E field as a deeper portion. Finally, in the shallow portion, only the horizontal induced current having westward direction can be remained. So you can measure such kind of induced current. Practically to say, you do not have a few chance to measure the induced current directly. You can only measure the induced electric field or voltage differences due to the induced current on the surface. Finally, due to such kind of AD electric field, the secondary magnetic field can be generated. Below the Earth, secondary field can try to cancel the primary magnetic field. However, on the surface, the secondary magnetic field will be added to the primary magnetic field. Anyway, if we put the magnetic sensor on the surface, so we can get both field, primary field plus secondary field. And if we put the voltmeter here, so we can measure the voltage differences due to the induced current. Again, we can measure the magnetic field. More politely to say, we can measure magnetic flux density, B, on the surface. And also, we can measure the electric field, not that unit, not volt per meter, millivolt per kilometer, very tiny amount of the electric field that can be measured by recorders. Also, we can focus the frequency of the fluctuation of the B field and E field. How? Well, there are various ways. Filtering, yes. But normally we use the Fourier transformation. After getting the time series of the magnetic field and electric field, we apply the Fourier transformation to get the amplitude of the magnetic field and electric field at one frequency, now F. So finally, we get the resistivity law based on this equation. Very simple. So if we measure the amplitude of magnetic field and electric field on the or electric field on the surface, and if we know the frequency, what we focus on, so such equation give us a chance to get the resistivity without any drillings. This law is normally called as apparent resistivity. Time is limited again. So if you have large interest, how to get this equation? If you love physics and mathematics, please check the appendix 2, 3, I forget, 3 maybe, appendix 3 in my slide. And the equations at the last of my slide, PhD file. Move on. How can we get depth information? The previous equation is pretty simple. Just a moment. Oh, okay, just a moment. Previous equation is pretty simple. We get the resistivity information, but how deep? Yeah, we can get the depth information. These are equations. If you have interest, again, please check the several slides attached at the end of my PDF slides. E field and H field is theoretically expressed by term of this one, exponential term. K is a kind of wave number. I is the imaginary number. What is this? Visually, I can briefly introduce what feature the equation has. In the high frequency induction case, this equation tells that the amplitude of induced field, both electrical and magnetic field, Z means depth. Z means depth. The amplitude is rapidly decreased exponentially. Now you can easily understand this phenomenon. Think about the mobile phone in the tunnel, or a mobile phone at the underground floors, or mobile phones in the huge concrete buildings. All of them, the tunnel or underground floors or huge concrete building can shut out the EM field. If the material have some conductivity or resistivity, the attenuation of the EM field can be controlled by the frequency and the conductivity. Focus on the frequency. High frequency EM field can rapidly attenuated towards depth. Think about the behavior of electron. Electron move right, left, right, left, right, left, left, rapidly. And due to such kind of rapid vibration, the energy can be used for the increasing of the temperature. So the high temperature result in the high attenuation of the EM field. How about the low frequency case? Low frequency, in a low frequency, the attenuation is not so rapid. So if we use the high frequency EM field, so we can get the shallow information. While if we focus on the low frequency fluctuation of the EM field, we can get the much deeper information. More people joined. Okay, go ahead. So think about the frequency dependence of the apparent resistivity. For example, 10 Hertz. What is 10 Hertz? Yeah, of course, you know. Within 1 second, 10 times fluctuation of EM field are observed. Okay, 10 Hertz. So apparent resistivity can be, again, calculated by this simplified equation. So 10 Hertz amplitude, magnetic field at 10 Hertz, E field at 10 Hertz, so the amplitude, F equal 10. Then you can simply calculate the apparent resistivity at 10 Hertz. Same at 1 Hertz, same at 0.1 Hertz. So you can get some change of the apparent resistivity through the frequency. It is so-called the apparent resistivity curve. What the curve means? Very simple. High frequency indicates the larger apparent resistivity, and low frequency indicates the smaller, lower apparent resistivity. So we can guess that the shallower structure has resistive feature and the deeper structure has conductive feature. Pretty simple. This is cartoon. This is true. This was obtained at a MT survey site in Japan. In this case, the Ogiri field is known as the Fuji Josemar field in Japan. And one of the sites located is in the surrounding cup. Okay, focus on the left panel. Again, frequency. So the high frequency to low frequency can be interpreted as the shallow survey to deep survey, right? You can find two curves. What is this? So this circle indicates Z, Y, X. Normally, it depends on the company or depends on the operator. X means north, not always. It is typically. Sometimes X could be selected toward east and Y could be selected toward north, but depends on the case. Or X is selected along the survey profile, and Y is selected perpendicular to the survey profile. But now X is north and Y is east directions. Repeat. And what's that? ZYX can be estimated from the EY field and EHX field, EN field and HE field. Divided, it is not mathematically true, but roughly to say, the ZYX can be calculated from the amplitude of north-south magnetic field and east-west electric field. So what is ZXY? Same. HYEX. Again, normally the north X same means, but it depends on the case of each surveys. Again, the XY can be derived from the north-south E field and east-west H field, magnetic field. As a result, we can get two different apparent resistivity curves at the same site. But both curves indicate a similar feature, high to low. At the shallow or high frequency ranges, apparent resistivity indicates thousands or several hundred ohm meter. As the low frequency case or deeper case, apparent resistivity indicates several tens of meter. So such condition is quite similar to this schematic condition. Shallow structure has a high resistivity, deep structure has a low resistivity or conductive feature. Such feature is commonly observed in the Josemar field. Why? I will again introduce the such kind of features in the case study chapter. Look at the right-hand side. Similar curves are obtained, but they are highly fluctuated at some frequency ranges. Think about the source of magnetic. This is not artificial one. This is natural source. The natural ionospheric current can make the fluctuation of the natural magnetic field and induced E field below the surface. So if you change the time of the measurement, you do not have any good responses at some frequency band now, the around 1 kilohertz. It is well known that the 1 kilohertz band and 1 hertz band do not have any high amplitude source field. It is truly come from the nature of the ionosphere or the reaction between the solar activity and the ionosphere. In the high frequency ranges, higher than the 1 kilohertz, there are several source field, natural source field. Between the 1 kilohertz to 1 hertz, there are another source field. And below the 1 hertz, there are another. But those frequency band, unfortunately, has a weak signal amplitude. It is so-called dead band. Dead band. Plus, if you get the MT data in the highly populated cities, you may have the very bad sounding curves. Of course, it is due to the human activities, artificial noises. And the natural field give us the great chance to get a deeper penetration. However, it is quite weak against the noises, especially as the frequency band of 1 kilohertz, around 1 kilohertz and 1 hertz. So how can we overcome this problem? Time. Longer time observation will give us a chance to get the better qualities, or skip this frequency band. Actually, you don't have to use all of frequency data, all frequency data. You can skip some of the low quality frequency band. Of course, you lose some of data, but you still have some of good data sets. This data was obtained in the nighttime, and this was obtained daytime. The daytime-nighttime difference can make such kind of differences in some cases. Okay, typical configuration of empty survey. Time is limited. Let's move to the case studies as soon as possible. Typical configuration of empty survey. You can post the recording system. And normal recording system has its own high precision clock, or GPS radio wave can be used for the time synchronization. GPS wave can be used for the positioning on the Earth, but not only for positioning, but the accurate time signal can be obtained from the GPS. Then you can find some lines. Those are mainly for the electrodes. And some of them are connected to the magnetic sensor, like this. We can set one empty site. How many hours do we have to work for setting of the empty site? 1 hour, 2 hour? Normally, 1 to 2 hours. 1 hour, 1 hour, 1 hour. But there are great difference from the seismic surveys. At the seismic survey, they have to, seismologists have to put the seismometer simultaneously. So the 10, 20, 30 seismometer are necessary to get the data. So in such cases, the observation cost is very high. However, for the empty survey, only 1 or 2 empty instruments are can be used. For example, one empty instrument is settled on a site. Then next day, move here. Next day, move here. Move here, move here. If you get the empty data at 20 site, so the 20 nights or 20 days are required. If you have 5 empty instruments, so only 4 days. If you have 20 instruments and a number of workers or students, then you can complete the 20 empty data set at 20 sites through a night or through several days. Then you can move the all empty instrument to the another area. So nowadays, the total number of empty stations in a survey area is greatly increased. 10, small. 20, small. 50, 100, or several hundreds empty data sets are obtained at one survey area. Flow for data analysis. Look at the details later in my slide. But there are 3 stages. First, data acquisition. Then we get the empty response function. What is empty response function? So apparent resistivity curve through the frequency. Then check dimensionality, skip it. And then make model for the resistivity structure to explain the observed empty response functions. Finally, based on the obtained model, we make the good interpretations to get some target information. What is inversion? There are various kinds of good textbook, so you can easily trace it. I will briefly explain what is forward and inverse problem. For example, we got the empty response like this. And again, I said that the shallow area has a resistive feature and the deeper area has a conductive feature. But how deep and how high resistivity? This is apparent resistivity. But remember that the apparent resistivity is not the same to the actual resistivity at a depth. So the how deep and what is true resistivity? So in such case, we need the inversion procedure. What is inversion? We got the data, such as the apparent resistivity at a frequency or throughout frequencies. And we got the same data at various portions on the surface. This is observed data, empty response. If we assume some structure, okay, some structure, then calculated empty response are obtained through the numerical simulations, numerical programs. So calculated response equal observed one. Oh, it is quite happy case. Such a priori structure is equal to the true structure. But it is quite rare case, of course. Observed response and calculated response has some discrepancies. So how can we minimize this discrepancy? So, or observed response can be translated to the optimal structure. So this is a forward program from the structure to the response, normally by using numerical simulations, numerical techniques. But it is not enough to get the optimal structure. So inverse transformation or inverse projection is necessary from observed data to the structure. This is called inverse. So the forward direction and inverse direction are summarized in this figure. In detail, how can we get the inverted result? This is this flowchart indicates the general procedure of the inversion. First, we normally assume the initial model for the resistivity structure, then calculate EM response, such as apparent resistivity, from this assumed resistivity structure. Then seek the difference between the calculated and observed apparent resistivity or other responses. Small, normally not. So large residuals. Then think on the modification of model. Modified model can be used for the calculation of the EM responses. Then again, check the difference between the recalculated response with and the observed response. Large residual. Such iterative process give us the minimization between the of the difference between calculated and observed response. Finally, if we get the enough small residual between the calculated and observed responses, then quit the inversion procedure, visualize the model. Whole process is called inversion. And this tiny process is called forward modeling. The forward modeling is a core for the inversion procedure. And time is limited. I will skip the detail, but the key component for the inversion is here. How modify the model? This is basically this is normally based on the least square method. Please check some textbook by yourself. Case studies. First, I will introduce the case study of the active fault explanation. There are various case studies related to the active fault explanations. And this is the one of the successful result of such kind of active fault explanation. Can you guess where? Where it is? Here is not Japan, in US. This is named as the San Andreas fault, very famous active fault. And this is also play an important role as the plate boundary, the huge strike slip fault. This is a famous transect. This is a famous transect of the San Andreas fault. Distance. This image do not indicate distance, but vertical horizontal race is 1 by 1. So the here is 2 kilometers in depth, and here is 2 kilometers in horizontal distance. No vertical exaggerations. And you can find some ticks, tick, 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 tick. These ticks do not indicate the horizontal distance scale, but indicate the location of empty sites. So many empty sites, 1, 2, 3, so many empty sites. Unfortunately, no empty site. Maybe due to the hard topography, in my guess, or no road available for the empty surface. Anyway, these ticks indicates the location of empty sites. So there are a number of empty surveys. 100? Not 100, but more than several tens. 20, 30, 40. So based on the apparent resistivities obtained at each site, they answer これ、運ソースかな。運ソース、multi-un source use the inversion schemes to get such kind of resistivity structure. Where is Sanders fault? Here, SF, Sanders fault. Here is a kind of topographic shape. Forget it. And San Andreas fault. So the you can find the land area, low resistive zone, just beneath the SAF, with resistivity of 1 ohm meter, less than 3 ohm meter, pretty low resistivity. Normally, the igneous rock having the lower porosity indicates the 300 ohm meter or more. 1,000 or 10,000 ohm meter are commonly obtained as such kind of low porosity igneous rock. So this area, how low? 100 times or 1,000 times lower resistivity are obtained just beneath the SAF, San Andreas fault. Based on this figure, together with the surface geological observation, the authors put the lines for the geological interpretation. Is it true? I don't know. Anyway, now those purple-colored circles indicate the microseismic activities. Interestingly, microseismic activity is not concentrated within the low resistive zone and located not just beneath the high conductive zone, but the side of the high conductive zone. Such kind of feature are often observed not only around the San Andreas fault area, but also the other active fault zone. There's no good explanation why such kind of high seismic activities are located outside of conductive zone and not below the conductive zone. Why Sanders fault indicates low resistivity? Everybody believes that the zone's high conductive, low resistive zone can be created due to the fracture zone, including fluid. Similar explanation was done in Japan. Most of you remember that huge earthquake in 2016. It is called as Kumamoto earthquake. The moment magnitude was 6.2, and every Japanese people, including seismologists, believe this is the main shock, or main shock. Then every seismologist brought their own seismometer to Kumamoto area. 2 days later, April 14 and April 16, 2 days later, much larger earthquake. So it having the moment magnitude of 7.0 occurred. So it is again named as Kumamoto earthquake. It became main shock. But first, the Japanese government names the earthquake as the 2016 Kumamoto earthquake. This was main shock. So it is a kind of twin earthquake. So the two main shocks were occurred. But from definition, main shock is the largest earthquake. Is the largest earthquake. This is the foreshock. Huge damage in the Kumamoto castles and some huge bridges and roads, and also highly populated areas. 2 years later, we brought our empty instruments to this area. This photo taken by myself. You can find some crank shaped on the field. Here is the active fault appearing as the Kumamoto earthquake in 2016. local people show me the photographs taken at the earthquake, just after the earthquake. At that time, you can find fractures, fissure-like fractures, crossing the rice field. Of course, the rice field do not have any crown-like shape. It has the straight shape, but relatively, the land moved towards the, in this case, left-hand side. So this is so-called the right lateral movement strikes report. Here is a neighboring shrine. Unfortunately, we can guess that here is the fault location. So the shrine is located just near the cliff created by ancient movement along the fault. And in 2016, again, the fault moved like this. So the right lateral movement makes the destruction of stairs. Fortunately, the building was remained. And now this would be still remained for the remember of this huge earthquakes. Kyushu area here, the hypocentral area here. What's happened at that time? I'm sorry, some of the word is written in Japanese, but Futagawa and Hinago faults are located at this area. Everybody know due to the based on the topographic features. So the here and the here. Here is the Futagawa fault zones. And here is the another fault zone, Hinago fault zone. The blue indicates the surface ruptures appearing at the Kumamoto earthquake, 2016. So a part of Futagawa fault and Hinago fault can create the rapid slip motion along the fault. And then the strong shaking can destroy the Kumamoto castle and other cities. It is the actual rough story of the Kumamoto earthquake. But in more detail, slip along the fault is pretty complicated. Rupture process deduced by seismic records indicates the non-uniform slip distribution. What is this panel? Here is the Futagawa fault and here is the Hinago fault, two faults. Along Hinago fault and Futagawa fault, you can find some colored areas. Red indicates 5 meters, blue indicates 0 meters. This is inferred slip distribution from the seismic waves. So full wave information of the seismic record give us a chance to get the heterogeneous distribution of slips. Yellow indicates the slip larger than 3 meters. So huge slips. You can find some huge slip at this area. Oh, which is deep? This direction deep. This direction sharp. So here is the surface place. So the surface location. And here is the deeper portion, but projected on the plane. Of course, the such kind of fault has dipping, but forget it. Just the simplified comparison between the distribution of fault to the map. Okay, you can find some high velocity, large slips with high velocity. But in more detail, you can find well, you okay, you can find the high velocity slip near the surface, while the high speed slip not near the surface but a deeper portion. Here and here, these two areas has the different feature on the slips along fault plane. It is deduced from the seismic rules. Similarly, this image indicates the geological observation or geographical observation. And as I said, as the earthquake, there are many fissures and fractures on the surface, not observed before the earthquake. So we can trace the surface distribution of fissures and fractures. Then we can get the dislocation. How large amount of dislocations? The right lateral successive movement makes the horizontal dislocation. Okay, here is the distribution of horizontal location, but figure is too small. In summary, large slip area was found here, while here is the smaller slip area. These area correspond to these area. High slip area deduced by seismic record corresponds to the surface huge dislocation, while this deeper slip area indicates the smaller slips on the surface. So there are two areas having different amount of slip along the fault, not only deeper portion, but also shallower portion near the surface. So blue indicates the large slip area, and brown indicates small slip area. Our question is quite simple. Why such kind of difference are generated, although these two areas is categorized along the same Futagawa fault zone? So we decided to get the empty data around this area. Photographs. Here is the volcano area, caldera. And most of the area covered by the harvester zones. So after the harvest season, we asked the local farmer to put our instrument through a day. So we used 4 instruments. We got the 20. Remember that the my photographs showing the clear left lateral, right lateral displacement here. So this area is categorized as a large slip area. We put the 1, 2, 3, 4, 11 かな。10 to 11, 1, 2, 3, 10 to 11 empty stations, and inverted gray triangle indicates the location of empty survey. And this is correctly called as a empty survey because the instrument is slightly different from the empty. And the frequency is also different from the empty. AMT is focused only on the near shallow structure, typically from the surface the depth of several kilometers. In this case, the penetration depth is about 1.5 kilometers. And through the inversion procedure, by using the observed AMT responses, render indicate the location of fault, not the MT locations. We guess the such kind of inverted resistivity mode. red indicates low resistivity. So 1 ohm meter here, 1 ohm meter. Blue indicates the resistive zone. 10,000 ohm meter here. Here is the logarithmic resistivity. So the red, orange, yellow, green, blue indicates the one order change of the resistivity, right? You can find the clear red zone here. It is located just beneath the surface fault trace. So we believe that that red low resistive zone should be related to the fracturing. So high fracturing, fracturing makes the high porosity, and the water within the pore spaces can decrease the resistivity, bulk resistivity of strata. So such kind of low resistivity is reasonable below the active fault zone, similar to this sun underscore. This transect from northwest to southeast. Not only the empty data at the large strip area, this one, we get the 3 different empty profiles. So line NSH is located in the smaller strip distribution, while OKO, remember that the Futagawa fault is located here and here, but as the earthquake, the surface rupture is obvious at this area. And the surface rupture is continued towards the south along another fault zone. Futagawa fault zone is identified from the northeast to southwest with the length of 30 kilometer, 40 kilometer, 50 kilometer. However, we do not have any evidences of the strip as the earthquakes. From the seismic record, no. From the surface observation, nothing. But we worry about the future occurrence of earthquake because the Futagawa fault zone is has the strip only as the northeastern portion. How about the southwestern portion? We have no idea, but at least we would like to understand the some quantitative estimation of fault movement. Fortunately, the MSK line having the large strip at earthquake indicates the clear low resistive zone, okay? So the Harvard line NSH, it indicates the smaller strip deduced from the seismic record together with the geological surface observation. Here is the fault ruptures at the earthquake. However, we, of course, find the some low resistive zone, but resistivity is much moderate than the large strip area, much moderate. It is quite reasonable because the high rupture, large strip rupture can initiate the high porosity, and it results in the low resistivity, while the small strip cannot initiate large porosity, and it results in the moderately low resistive fault zone. Okay, how about third area, OKO? It only indicates quite tiny conductive zone. How about the scale, depth scale or width? quite narrow and small one, and have the resistivity not so low. So from these implications, we can say that the OKO is located to the Futagawa fault zone, but the activity around this area should be lower than these areas. More safety? I'm not sure, but such kind of quantitative evaluation of fault activity, not relied only on the geological surface observation, would be quite useful for the future hazard estimations. Fault slip and evolution of damage zone. It is a kind of model deduced, estimated from our results, three different resistivity structures. First, the damage zone should exist before earthquake due to the repeated earthquake activities. And it can be characterized as high porosity and high water content. Those areas should have the lubrication along a fault. So it results in the large slip and strong shaking at a large earthquake. Due to such kind of large slip, the damage zone should be evolved due to fracturing. So the larger damage zone can be created. Larger damage zone can give us the large lubrication, then large slip can initiate the much larger damage zone. Such kind of circles can make the low resistive fracture zone, and it have the potential for the large slip with the strong shaking. While moderately low resistive zone along the fault do not have the high potential to the large slip and the strong shaking. That is our implication. And now we are preparing the paper would be submitted to international journals. Future. Okay, we got such kind of detailed subsurface structures. So what is next? Fortunately, and recently, we have a chance to get the numerical simulation of fracturing. Such simulation was done in our laboratory based on the discrete element method. And we assume the weak zone here. This is 3D view. This is plane view from top. And the right lateral movement is appended to such kind of 3D model. So what's happened? Blue indicates the generation of the cracks. And before, at the initial stage of the simulation, initial stage, this is final stage. Initial stage, this is just a GIF animation. I cannot control it. おまだ行くのこうやってこれ。At the initial, there are no cracks. But after the time, the evolution of the fracture can be created. This is not a real one. This is only in the computer simulation. But such kind of distillation is quite similar to the echelon faults often observed in the geological surveys. So we can get such kind of quasi-laboratory experiment in the numerical simulations. So if we assume the much detailed subsurface structure based on the resistivity, so what's happened? So such kind of feature or such kind of story can be realized by using the help of the numerical simulation. Another case study, volcanoes. This is quite a nice illustration how resistivity is useful to understand the hydrothermal circulation around the volcanoes. First, temperature. temperature goes up, 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 up to the deeper portion. Vertical axis, you do not find any vertical axis, but vertical indicates depth. Depth. At the deeper portion, temperature goes up, of course, due to the some heat energy resources, such as magma chamber or something like that. What's happened on the resistivity? Resistivity goes first down. In case of saline water or fresh water, both resistivity goes down, 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 and down. Then goes up. What's happened? Note that the temperature from 100 degrees Celsius to about 200 Celsius, such temperature range, in the such temperature range, the smectite clay can be well established, well formed. And a much higher temperature range, another clay mineral such as carbonate, or in this case, chlorite or something like that. And remember that the resistivity of rocks or conductivity of rocks, smectite clay indicate quite low resistivity feature, low resistivity, while the other clay mineral do not indicate low resistivity feature. In other words, the resistivity can have the pretty low feature as the smectite zone. Such kind of cartoon indicate what I said. So the smectite or the temperature range from the 100 degrees Celsius to the 200 degrees Celsius can make the low resistive clay cap. Of course, we need the water to make the clay. Only the high temperature can be, but formation of clay is limited. Is it true? This is the result from the volcanic drillings in Japan, Unzen volcanoes. Temperature, depth from 0 to 300 meters. Okay, temperature goes up, 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 and then down. Such kind of temperature trend. Permeability. Permeability is also goes down, 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 and up. Note that the horizontal axis. It strongly implies that such kind of low permeability due to the clay minerals. And from the 100 degrees Celsius, much higher temperature range, it is suitable for the smectite clay formations. How about the electrical conductivity? Shaded area indicates the resistivity structure deduced from the MT survey. In the MT survey, at the surface area, this is conductivity. In resistivity, 100 ohm meter or higher are commonly observed in the surface area in volcanic regions, while resistivity goes down to 1 ohm meter due to clay, then recovered. In this case, the temperature becomes degrees. So that is a major reason why MT-derived resistivity goes up again to the 10 ohm meter. These circles indicates the laboratory measurement of the surface conductivity together with pore water. Another case, and this is a comparison between the borehole loggings. In the borehole, we can measure the resistivity directly, together with the material observation. In the borehole SZ4 and SZ2 neighboring boreholes, at where, I forget, maybe somewhere here. I'm sorry. different here. And we can get the borehole-based resistivity data. So very detailed resistivity data. And the solid squared line indicates the resistivity structure obtained from the MT data. This is the structure from the MT data set by using 3D MT inversion. Note that borehole information is not used for the 3D MT inversion, so the independent data set. But we can guess the quite good similarity. Resistivity 1, 10, 100, 1000, quite a good similarity between the MT-based resistivity and the borehole-based resistivity. And again, as the lowest resistivity region, smectite minerals were observed along boreholes through the quarries. So this is the schematic view of the hydrothermal circulation. First, in the resistivity, deep magma has the low value. It should be related to the magmatic fluid, magma itself, or fluid released from magma. And normally, it indicates the low resistivity, lower than 10 ohm meter. Hydrothermal circulation can make the clay-rich areas. It is so-called clay cap. Hydrothermal alternation can make clay cap. And again, it should have the lower resistivity than the 10 ohm meter, in typically 1 ohm meter or less. This also has a low permeability, so the hydrothermal reservoir would be created at this portion to capture the hot fluid, hydrothermal reserve. However, it do not indicate the low resistivity because this area indicates extremely low resistivity, and based on the feature of MT survey, the underlying low resistivity zone but having the higher resistivity than covering zone do not image it clearly, does not image clearly. So the in general, such kind of hydrothermal reservoir do not have low resistivity, but a lower resistivity than surroundings. So moderate resistivity below anticline can be typically identified as the hydrothermal reserve. Is it true? So the three examples will be introduced. First, AMT survey around Mount Fuji. Mount Fuji is quite a beautiful mountain, and if you have a chance to come to Japan or Tokyo, you can easily find it because the Rapid Express Shinkansen connecting the historical city Kyoto and metropolitan Tokyo is located just close to the Mount Fuji. You can easily find the Mount Fuji from the Shinkansen Express. And there are a number of MT surveys, now I can introduce the one transect along this line. This one was published in the GRL 2004. You can find the summit of the Mount Fuji, 3,000 meters, 3 kilometers, quite tiny relative to the cluster scale. Circles indicates the microseismic activities, and the stars indicate the seismic activity, but far from the conventional one. Those are low-frequency earthquakes. Often observed beneath the summit of volcanoes, not only in Mount Fuji, but all volcanoes in the world. It should be related to the volcanic activity, probably the released fluid from the magmatic chambers. C1 is just located beneath the Mount Fuji. Again, red indicates the low resistive and blue indicates high resistive. So it should be related to the magma chamber, deep magma chamber. And released fluid might be related to such kind of low frequency earthquake. There is no other huge magma chambers. What is this? I don't know. Slightly far from the summit. And the author, Aizawa-san, do not mention such kind of features. But it is far from the summit, so that it is not related to the magma chamber itself. Okay, next, focus on the much shallower part. I'm sorry. This is the interpretation, not by Aizawa-san, but as a seismologist. Volcanologist, I forget. Another mountain, Mount Fuji is located here. This is the another mountain named Hakone. Hakone, much smaller, but more active than the Mount Fuji. And in this case, we set a number of AMT surveys here, 30, 40 AMT surveys. And I'm co-author of this paper. And now I can show you the transect as the east-west transect near the summit. Summit is here. Here is the famous Owakudani hot spring area. The huge steam fumaroles are observed, and many tourists are visiting with egg, you know. Many places put egg in the fumaroles. Then steamed egg can be obtained. This is the transect as such kind of steam area. Fumaroles here. And depth 1 to 5 kilometers. Oh, very shallow relative to the transect beneath Mount Fuji, but a much detailed structure. Fumaroles area is located as the land geological strata, not geological, low resistive anomaly. And such shape is strongly suggests that it would be the hydrothermal altered clay. So here is the, here is the reservoir. Is it true? Maybe. This black dot indicates the microseismic activity. Microseismic activity will moved from the deeper portion to shallow portion in 2012, I guess. 2012, yes. So the this MT campaign was conducted just after such kind of seismic event. That is the main target for us. So through these seismic events, gas fluid should come up. So here should be the hydrothermal reservoir. Finally, move to the Indonesian Josemar field. Here is a famous Indonesian Geosomal field, wire wind. Of course, most of audience know what is wire wind. So Bandung, wire wind, Marubara. And through the previous surveys, geophysical surveys, gravity and magnetics, 1, 2, 3 different geothermal reservoirs or geothermal areas are reported. Now we focus on this area. 3 years before? Before COVID-19, we got the AMT data at 38 sites. And at that time, the electrode dipole distance is quite tiny, only 0.6 meters. It is mainly due to the limitation of land use. So actually we can extend the length, but as a trial, only 6 centimeter dipole length is adopted in this survey. This is magnetic sensor. horizontal and vertical electric sensor. Now we only focus on the north area. In the south area, you may have a question why we do not put any empty sites at this area. Pretty simple. Here is the Josemar plant, noises. Here is high voltage power lines, noises. We have no chance to get data at this area. Actually, some of the station indicates the pretty low data quality. But we get data here. Next time, we may have a chance to get data around there. This is a photograph when we take the data. At that time, only 3 minutes were used for getting the data acquisition. One night? Better, but we decided to get data at many sites as possible. So here is the geothermal power plant. You can find the steams coming from the geothermal power plant. Okay, we got the three-dimensional subsurface structures. Now we do not pay any attention to the topographic reliefs. It should be included, but it is a kind of a pre-version, test version for the 3D inversion. We, of course, have to put the topographies on the model, but not included in the 3D inversion results. And very complicated. Now we only focus on this structure, east-west transect here. Such kind of structure is similar to the schematic structure what I showed before, or resistivity structure below Mount Hakone. You can find some continuous low resistive zone here. So in the textbook, in the textbook, here should be the reservoir, and here should be the clay. However, there are some resistive features. Interpretation. Of course, this is a kind of preliminary interpretation, and we need much information from the borehole observation. Of course, there are a number of borehole observations. And the fracture analysis, the surface topography, give us a chance to get the lineament information, and the fracture density can be discussed. And geochemical information, it is important because along fracture, we get the geochemical signatures. Now we are trying to compile all different kind of geological, geochemical, and geophysical data set. This is a kind of tentative one. You can find low resistive features. Those areas indicate quite low resistive features. So those low resistive features in the volcanic area should be interpreted as clay caps. Clay cap. These clay caps especially for this one, have the narrow low resistive zone. It might be related to the hydrothermal altered clay zone along fracture zones. Normally, the high temperature gas and fluid can come up through the fracture zone. So the clay alteration or altered clay would be concentrated along fracture zone. So those areas might be related to the reservoir. but there's no horizontal horizontally expanded low resistive layer. No low resistive layer are found. It is also related to the fracture zones. So focused fluid along the fracture zone can make the hydrothermal clay-rich zone plus isolated reservoirs. This is my own interpretation. Again, I would like to discuss with my colleague in Kyoto University or ITB whether such kind of interpretation is real or not. What was obtained previously? This is the empty structure in wire wind. Note that this direction of section is different, south-north directions. But forget it. In the previous one, you can get the broadly distributed low resistivity features, typically 2 ohm meter. It should be clay cap and well written in similar to the clay caps well written in the textbook. So here should be the reservoir. And a much higher resistive region will be interpreted as intrusive rocks. However, note that the spatial density of the observation site, empty site, 1 kilometer spaces or more. Back to this case, in this case, the average spatial distribution between the empty site would be the 500 meter or less. In the closer case, the only 50 meter separation was done in the dense empty survey. So in my conclusion, much denser observation should be necessary now to discuss the detailed structure below the hydrothermal area. Conclusion. Damage zone along faults indicate low resistivity. In the hydrothermal area, the clay cap layer indicates the extremely low resistivity. The hydrothermal reservoir below the cap layer is often imaged as a moderate low resistive zone, basement rock resistive. So in this condition, EM survey is very effective for finding clay or water-rich or lithological units, and also the evaluating subsurface structure with using such kind of detailed feature, but not only from the empty data set, but also from the other research, such as computer simulations of rock fracture in the hydrothermal circulations. I showed the numerical simulation of rock fracturing. It will be helpful for the interpretation of resistivity structure around active fault. Also, the hydrothermal circulation, often done recently, will be quite useful for the understanding of the complex resistivity structure below the hydrothermal area. For the problem, there are many further problems, but I would like to emphasize the detailed structure with the higher resolution will give us much good information, especially the on the discussion with the geologist and geochemist. Conclusion. Okay, 12 minutes are left, so I'm very welcome to hear the questions from audience. I'm sorry, I cannot catch up the chat. Does somebody help me to pick up the questions? Now I'm checking chat. Just a moment.
You finished with your conclusion?
Yes.
Okay, yeah. Now question and answer session. So please read the questions here. There are two.
Okay. Yeah, I catch up the chat. I missed some of the questions through the chat, but there. This is first one. Maybe, if not later, please ask me directly. Okay, the question from Dela Pulatamanobia Putura. The question one, how does the coherence between electrical and magnetic field affect the quality of magnetic data? Good question. The coherence means the similarity between the time series data between the electric field and magnetic field. Yes, and we always check the coherence between the E field and H field, the electric field, magnetic field, because low coherence data implies that some troubles. For example, the magnetometer was not connected to the recorder, or the animals cut the line. So they are, of course, and the artificial noises can make the low coherence. But not only the coherence, but also the other features should be included to check the data quality. But coherence should be higher than, of course, 0.5, 0.6, 0.7. Much higher coherence data should be dealt in the inversion procedure. Question 2, can the integration between the magnetic resistive memory and the subsurface model from the other geophysical method? Of course, yes. For example, one of the good combination on the MT and seismic survey may come from just a moment. Okay. Can you watch this slide? Oh, わかった。これだ。For example, such kind of image is not a sharp one. Quite vague. For example, if we want to pick up the boundary between the high resistivity and low resistivity, but it is quite hard for us. Why? We do not put any constraint on the lithological structures. If we got some of the, for example, the boundaries within the sediment area or in the basement rock from the seismic survey or lineament analysis, geological data, borehole data, and so on. Of course, we can put some of the sharp boundary in the structure. Such kind of sharp boundary greatly improves the image. Actually, data can be well explained both for the smooth model or model having the sharp boundary, same level. But for the geological interpretation, such kind of smooth model might be difficult for geologists. So such kind of combination is quite important. Same from the gravity data. Gravity gives us a chance to understand the thickness of the sediment layer. So the thickness can derived from the gravity can be put. And more advanced joint inversion scheme in the various kind of geophysical data is also helpful. Okay, next question from Irfan Prasetcho-san. What I want to ask that in the geothermal system, there is a recharge area. Good question. For the case study in Kyushu, Japan, where is the recharge area? Good question ですね。Recharge area cannot be imaged directly from the resistivity. For example, Kyushu. This is also same. Yeah, I discussed the recharge area based on the resistivity. But from the only from the resistivity data, no chances. However, think about the mechanism of the discharge and recharge of the hydrothermal fluid. Fracture should have the key. And the fracture distribution can be obtained from the geological observation or lineament analysis based on the digital topographic data sets. And if there is the clear fracture zone or clear lineament, but we do not have such kind of low resistive feature. So in my understanding, such area has a high potential for the recharge zone. Such requirement is quite high because the discharged hydrothermal fluid should be returned to the deeper portion. So the recharge problem is also huge in the Japanese geothermal power plant system. Another question. So there are only the magnetic, we have no chances, but the combination between the fracture distribution analysis, lineament analysis, so we may have a chance. Could you explain? Next question, Harumita Lestari Sam. Sam is Miss or Mrs. Mr. in Japanese. Could you explain more about the earthquake precursor through the EM observation? Earthquake precursor. Such is far from my talk, but do not believe that the curious EM signal will be the precursor of earthquake, because there's a pretty many variations of EM signals, natural one and artificial one. Which is the EM signal for the earthquake, epicentral areas, hypocentral areas? No ways. So the many people, many people tried to identify such kind of signals. Scientifically, there's no chance to identify the EM precursor signal right now. In future, I have no idea, but at least it is very hard to identify the source of EM signals solely from the EM waves, observed EM waves. What is next? From Litska. Your empty process results are very good. Thank you. What special method do you use in processing this empty data? Nothing. And we use the Phoenix geophysical systems, and the software is normally bundled. We just only use the bundled software to the instrument. However, we, of course, have some difficulty to analyze the data in the high noise area. For those problems, we have developed our own new schemes for the empty data acquisitions. If you have interest, please ask me. I can introduce the paper published last year. And another question. I'm sorry if I skip your question in chat. Please allow me. Question session will soon end. Photo session. Okay.
There is still one question, I think.
One question. Okay. Come on.
Oh, I think time is over, Professor Goto. So thank you very much for your interesting lecture, and we appreciate it very much. Yeah. Well, now before this session ends, please stay here for photo session.
Oh, of course, of course.
Yeah, and Ms. Harmita.
And last, just 30 seconds for advertisement. And as you may know, so the Japanese community holds the huge meeting relating to the Earth planetary science named JPGU. And next year, JPGU 2022 May, we will have the international session relating to the EM survey. And how deep? Any depth. What's purpose? Any purpose. the JPGU 2022 will be held in Chiba or Yokohama, I forget. But online session is also held. So in our session, the both presentation online or offline we welcome. So if you have interest to this meeting session, please send email to me. And plus 2024, we have EM huge workshop in Japan. Beppu. I believe Indonesian people love the volcano and onsen. You can enjoy the such kind of field in Japan. Thank you. And those two slides are also included in my PDF file. Thank you so much.
Okay, thank you very much. So we will interested in your next seminar, and hopefully we can join you. Okay. Yeah, and now, photo session, please, Harmita.
Okay, everyone, please turn on your camera. Thank you, Prof. Tada Norigoto, for the very interesting lecture. Okay, we start from page 1. 1, 2, 3. The next page. 1, 2, 3. The last one. 1, 2, 3. Thank you, everyone. See you in the session 2 tonight.
Thank you, Ms. Harmita. So this session, I close the session, and thank you very much for your lecture, Professor Goto, and we hope we will meet again in the next time. Yeah, and thank you also for all participants. Yeah, there are almost 7 participants in your. So
I'm very happy to meet the many people in the Indonesia. And if you have questions, please send an email to me. Don't hesitate, and I will give another additional documents or papers to you. Thank you very much.
Okay, you're welcome. Thank you, Professor Goto, and thank you for all. And this room will be closed by me. Thank you.